Salam everyone! In the last episode, we introduced forecasting methods. In today's video, we'll dive into data distributions to gain a deeper understanding of each one. We will focus on a subset of distributions that are primarily used when analyzing time series data. The subset includes the following distributions: normal, uniform, binomial, Bernoulli, Possian, exponential, and joint distribution. Normal distribution. It has a famous bell shape. In a normal distribution, the mean, median, and mode are all the same. The distribution is symmetric, as half of the data lies below the mean and the other half lies above it. About 68.2% of the data falls within one standard deviation of the mean, 95.4% within 2, and 99.7% within 3. Data beyond 3 standard deviations, known as 3 sigma, are rare and often considered anomalies. Nature provides many examples of normal distributions, such as blood pressure. In a healthy population, blood pressure typically follows a normal distribution, with most people having readings near the average, which is like around 120/80, and fewer having very low or very high readings. While a normal distribution is perfectly symmetric, skewness is a measure of how much a distribution deviates from this symmetry. In a normal distribution, skewness is 0, indicating no skew. If a distribution has a longer left tail, it is negatively skewed or left skewed. But if the right tail is longer, it is positively skewed or right skewed. Another important measure in this context is kurtosis, which evaluates the shape of a distribution, focusing on the tail and the concentration of the data around the mean. A normal distribution has a kurtosis of 3 and is also called mesocortic. It has a moderate peak and a standard tail. Distributions with sharper peaks and thicker tails, where the data is more concentrated around the mean, are called leptocortic, with kurtosis greater than 3. On the other hand, distributions with flatter peaks and thicker tails are called platycortic, with kurtosis less than 3. The terms lepto, meso, and platy are derived from Greek words, meaning thin, middle, and flat, respectively. The formula of a normal distribution is as follows, where x is the value of the variable or data point being examined, mi is the mean, sigma is the standard deviation. Uniform distribution. It is a type of a probability distribution where all outcomes are equally likely. As you see, it has a rectangular shape, flat shape. Uniform distribution has the following formula, where it is defined by 2 parameters, A, the minimum, and B, the maximum. An example of a uniform distribution is rolling a fair die, where the possible outcomes are 1 through 6. The probabilities of getting those outcomes are equally likely, and that is the basis of a uniform distribution. Binomial distribution. The binomial distribution models the probability of a value taking one of 2 independent outcomes, such as success or failure, under a specific set of conditions. Those conditions are: each trial results in only one outcome, success or failure. All trials have the same probability of success. The trials are independent of each other. Let us look closely on a binomial distribution. X-axis represents the number of successes denoted as k in a given number of trials n. Y-axis represents the probability of achieving exactly k successes in n trials. As an example of binomial distribution, let us consider flipping a coin 100 times. The expected number of heads would be 50, or simply 100 multiplied by 0.5, because there is a 50% chance of heads on each flip. Another common example is estimating a basketball player's free throw success rate. where a made basket is considered a success, 1, and a miss is considered a failure, 0. The Bernoulli distribution. Bernoulli distribution is a discrete probability distribution that models a random experiment with exactly 2 possible outcomes, success, 1, or failure, 0. It focuses on binary outcomes, where there are only 2 possible results for each trial. This distribution is used to describe a single trial of a binary experiment. In fact, the Bernoulli distribution is a special case of the binomial distribution, where only one trial is conducted, which means that in this case, the number of trials n equal 1 in a binomial distribution. Example of Bernoulli distribution is email spam detection. When you receive an email, it is either marked as a spam, which we can label as 1, or not a spam, labeled as 0. The probability of an email being spam depends on the algorithm used by the spam filter, and the probability of it not being a spam is simply 1 minus that value. Exponential distribution. Before we dive into exponential distribution, let us first understand what a Possian process means. Possian process is a statistical model used to describe random events happening over time or space. The key features of those processes are independence. Events do not influence each other. Constant average rate, meaning the likelihood of events occurring remain constant over time. And notably, events are spread out, so simultaneous occurrences are rare. Possian process is widely used in areas like customer arrivals, network traffic, or even modeling natural events. It is simple yet powerful for understanding random phenomena. Now, let us look at the exponential distribution. This distribution models the time between events in a Possian process. In simple terms, it tells us how long we might wait before the next event happens. The shape of the exponential distribution is a right-skewed curve, starting high at x0 and gradually decaying as the value increases. The key feature is its memoryless nature, meaning that the probability of an event occurring in the future is independent of how much time has already passed. It is commonly used in scenarios like predicting the time until a machine breaks down or the time between customer arrivals in a queue. The probability density function, PDF, of an exponential distribution is the following, where lambda is the rate at which events occur. 1 over lambda represents the average time between those events. The last distribution on our list today is the joint distribution. In simple terms, it describes the probability of 2 or more random variables occurring simultaneously, showing how they relate to each other and how the output of one random variable are distributed given the information on the outputs of the other random variables. For example, we might look at the probability of rain and the probability of someone carrying an umbrella at the same time. We often write this as P of x and y for discrete cases or f of x and y for continuous ones. The key idea here is that joint distribution shows us if and how those variables are related. It can be visualized as of a table for discrete cases or a heat map or 3D plot for continuous data. Joint distribution has many applications, especially in the field of machine learning and data analytics. In time series analysis, joint distribution can help us understand the relationship between a variable's value at different time points. For example, consider daily stock prices. The joint distribution of a stock price on day 1, x1, and day 2, x2 shows how likely certain combination of prices are to occur, such as x1 equal 100, x2 equal 105 the next day. This helps identify dependencies, like whether a higher price on one day increases the chances of a higher price on the next day. That's it for today. In the next episode, we'll dive into some essential concepts in time series analysis, such as stationarity and autocorrelation. Stay tuned and I'll see you then. Salam.